Okay, ladies and gentlemen, what we've been looking at is measures of location. Okay, so we just looked at a z-score, and that z-score was looking at an individual's observation and where is it within that location compared to the, or within that distribution, excuse me, compared to the mean. Okay, if we, or when we are dealing with a normal distribution, we can actually look at that observation and we can look at that percentile associated with that. Okay, so what do I mean by that? The normal distribution, you may have heard of the standard bell curve, okay, or a standardized test. If something comes from a normal distribution, which we'll talk about when that happens and how often that happens, that actually happens a lot more often than you would think. The distribution of all of the observations, okay, is normal. And what does that mean if it comes from a normal distribution? That means all of the observations, if I would take everyone's ACT score, right? And I would make a dot plot, right? You can imagine it, right? I'm gonna keep going, right? It would fill this whole thing up. We would have the bell curve. We would have a nice symmetric distribution. Why? Because the ACT scores are normally distributed, okay? Lots of distributions of observations are normally distributed, which means we get a nice bell curve like that. Now, why does it matter? Well, in statistics, we like to draw conclusions about populations and then make decisions based off those conclusions, okay? We summarize what's going on and we say, are we comfortable with that or not? So let me talk about what kind of conclusions we can draw when things are normally distributed. Now, the first thing, we need to backtrack just a tiny bit. We have found summary statistics. We have found an X bar, and that means we have found a mean. And that X bar is the mean for a sample, not for a population, for a sample. That is associated for a sample. If I took a sample of 10 kids from Armstrong and took their ACT score, I could find their X bar, their mean. That's not based off the population of Armstrong kids. Same thing with an SX. I could take a sample of 10 kids from Armstrong, find their ACT score and their standard deviation associated with it, right? But that's not for the whole population of Armstrong students. When we're talking about population, okay, and something's normally distributed, right there, smack dab in the center, that represents the mean of the distribution. But we don't call it X bar anymore because it's not describing the sample. It's describing the population. So we actually call that mu. It looks kind of like a cursive M or a U with really long like legs there, right? That is the mean of the standard deviation. Now, in a normal distribution, what we do then is we can measure 1, 2, 3 standard deviations above the mean, and 1, 2, 3 standard deviations below the mean. Now, a standard deviation for a population is not SX, it's actually called sigma. So this is 1 standard deviation above the mean, 2 standard deviations above the mean, and 3 standard deviations above the mean. Now, you will never calculate sigma, okay? And you will never calculate mu. That will be given to you. You will calculate summary statistics, okay, based off of a sample, but you will not calculate this. It will be given. Now, we also measure 1 standard deviation below the mean, 2 standard deviations below the mean, and 3 standard deviations below the mean. Now, how do I know where these numbers go? Now, I just did a quick sketch, but technically, guys, those of you who have taken calculus, on a normal distribution, that first standard deviation comes from the point of inflection. I don't know if that's the exact point of inflection, but that is technically where it comes from. Now, it doesn't matter in AP statistics, but for those of you who are calc hungry, I just wanted to let you know where that technically should go. All right, now next, let's put it in some context because you're looking at this and you're thinking, what? So once upon a time, the ACT had an average of 21 with a standard deviation of 5. Now, this is describing the population, okay? So what does that mean for our curve? What we would do is we would mark 21 right here in the center. And then 1 standard deviation above 21 would be plus 5 then, right? So 21 plus 5 is 26. And then we can do it again, 2 standard deviations above the mean, or it's just one more from the previous one. So we just add 5. So we're going to be adding 5 because that's 1 standard deviation. Here's another standard deviation above the mean. So let's add 5 again. Okay, so we're at 31. And let's add 5 one more time. So we're at 36. Okay. And then let's go backwards. So we have 21 minus 5. Okay. So 21 minus 5 would be 16. 16, then we're going to go down because we're below the mean, right? So down by 5 again. So that's going to give us 11. And down by 5 one more time, and that's going to give us 6. So here's our distribution. Now, this I made up. I think it's actually like 4, it was like 4.9 something, but it just makes it for easy math when I'm making a video. Okay, when I'm in class person to person, it's a little bit easier to do, you know, some of those other calculations. Doesn't matter, okay? Now, what you need to know now is there's something called the 68, 95, 99.7 rule, which means 68% of people fall within the first standard deviation of the mean. That means based off this distribution, 68% of people, okay, will get an ACT score between 16 and 26. 95% of people, okay, 95% of people will fall within 2 standard deviations of the mean. Now, this is true. This is called the empirical rule, the 68, 95, 99.7 rule. For all normal distributions, you can track the mean and the standard deviation, and you can draw conclusions that 68% of people taking the ACT will be between these two numbers. 95% will be within the second standard deviation. And finally, 99.7% of people will fall within, oh, that's not a very good 9. Will fall within 3 standard deviations of the mean, okay? Now, let's talk about this even more. So we're drawing conclusions here. 68% of people got between 16 and 26 on the ECT. 95% between 11 and 31, and 99.7 between 6 and 36. Now, this should actually be like 35 point something based off if it was 4.9, let's say. Can you get above the third standard deviation and below the third standard deviation? Yes, but it's incredibly rare. Think about the people who have a perfect ACT. That's incredibly rare, okay? So that's where that missing percentage is of that 100%, okay? That's where that is. If you have questions, write them down. Make sure you let me know. Now, on AP Stats, this is just a very sliver, okay? Sliver of the AP test. Because guess what? This 68, 95, 99.7 is actually an approximation, okay? It's actually like 68.86, I believe, or 81. And we're going to look at that. But we could base like just some general observations on here. Just so you know, this area right here, now I'm talking about the area under the curve for you calc people. This area here, anyone who's scored, right? You can imagine a bunch of dots. There's a bunch of people who scored between 21 and 26. In fact, that's 34%. 34%, we can break that 68 up between 21 and 26, which means 34% were here as well. Between a 26 and a 31, that area, the people, you can imagine all the dots of people scoring between, if it was a dot plot, between 26 and 31. Only 13.5% of people will get there. 13.5% of people will be between the first and the second standard deviation. And again, where are these numbers coming from? If you care, it is coming from calculus. And the same goes over here, 13.5. Now, remember, it's rare. It's hard to get above this. In AP Stats, if you score above a 2 for a normal distribution, a z-score of 2, which is this second standard deviation, or -2, that's rare. That's hard to do, right? And you can see that here between a 31 and a 36. That area there is 2.35%. 2.35% of people or individuals in a normal distribution, what their location, their observation will fall within the second and the third standard deviation. And the same is over here. Okay, so what should your main takeaway be from this slide? Hey, a lot of distributions, meaning everyone's observations all marked up together, looking at it, right? Okay, if I did a dot plot, we've learned how to do a dot plot. If it is normally distributed, you will have a nice symmetric curve. The mean of the distribution will be in the center, okay? When we're drawing conclusions about that population, okay, we can go 3 standard deviations up and 3 standard deviations below. We can say 68% of that population will fall within that first standard deviation of the mean. 95 will be within that second standard deviation of the mean. And 99.7 will be within the third standard deviation of the mean. I'm done with this section, part 2, okay? If you have any questions, write them down and we can talk about them in office hours or class. Have a great day, you guys.